Welcome to the Explainer Hero. We really take it for granted that when a massive fault occurs, our completely interconnected power grid doesn't just instantly collapse into total chaos. The secret to preventing that entire system from going down isn't just massive, bulky transformers, it's actually this incredibly elegant mathematical filter. So today, we're decoding grid chaos by taking a close look at symmetrical components. Let's get right into it.
Okay, let's dive into this. Picture this scenario. A huge, heavy tree branch snaps and crashes right onto a high-voltage line. Instantly, the physical stakes for the grid skyrocket. In literally a fraction of a second, the perfect, beautiful harmony of the system is violently disrupted, and it sends these chaotic fault currents just racing down the line. If our protective systems can't instantly make sense of all this chaos, some massively expensive infrastructure is at serious risk.
Now, to actually analyze that chaos, the source material reminds us that we have to start with our baseline of order. In a perfectly balanced, healthy three-phase system, the currents are exactly identical in magnitude and they're separated perfectly by 120 degrees. It's a flawless, perfectly synchronized baseline, kind of like a finely tuned engine humming along. So, to break down exactly how engineers decode this really dangerous grid chaos using math, here is our roadmap. First, order meets grid chaos. Second, the symmetrical solution. Third, positive versus negative sequence. Fourth, zero sequence and grounding. And finally, the mathematical matrix.
All right, let's kick things off with Section 1, Order Meets Grid Chaos, a system disturbed.
So when a severe unbalance like a fault hits, that perfect 120-degree spacing, it completely goes out the window. The currents become totally unequal in magnitude, and you get these jagged, highly unpredictable phase angles. We're essentially left with three extremely chaotic variables, IA, IB, and IC. A standard protective relay, just looking at that raw, messy data, wouldn't have a clue whether it should trip a breaker to save the system or just let it ride.
And that brings us to Section 2, the symmetrical solution, splitting the mass through a brilliant engineering pivot.
The source material highlights symmetrical components as the absolute hero of our story here. Invented over a century ago, it's basically a magical mathematical translator. It takes those messy, chaotic, unbalanced real-world currents and splits them into three distinct, perfectly balanced sets of virtual currents. It literally filters pure, dangerous noise into clean, actionable signals. So, what exactly are these virtual sets? Well, let's meet the first two personalities of our mathematical filter in Section 3, positive versus negative sequence, two opposite sequences.
Now, what's really interesting about this slide is how these two sequences behave so completely differently when put under pressure. The positive sequence is our good citizen. It represents the normal, healthy ABC rotation of the grid. But then you have the negative sequence. The saboteur only rears its head during a system unbalance, like a line-to-line fault. And crucially, it rotates backward in an ACB sequence.
And that backward rotation, it brings some incredibly urgent high-stakes danger. When these negative sequence currents flow into rotating machines, think massive power plant generators, they create a reverse rotating magnetic field. Listen, this isn't just some abstract math error. It literally acts as a physical brake grinding against a massive steel rotor. That generates immense friction and severe overheating. If it isn't filtered and shut down fast, it can melt a multi-million-dollar generator from the inside out. Absolutely catastrophic.
Okay, moving right along to our third virtual set in Section 4, zero sequence and grounding, the escape artist.
Now, this sequence operates under a totally different set of rules and presents a really fascinating puzzle. The zero sequence is made up of three currents of equal magnitude that have zero phase displacement, meaning they are perfectly in sync. And because they're completely in phase, they don't just cancel each other out like normal currents do. So where exactly do perfectly in sync currents go?
Well, they add up and actually escape the normal circuit. Zero sequence currents only flow when a path to ground exists. They completely bypass the standard routes, flowing straight through the neutral wire or literally through the earth itself. Because of this, spotting zero sequence current is the ultimate alarm bell. It instantly tells engineers, hey, we have a line-to-ground fault. So now we've got our positive, negative, and zero sequences. Let's transition into the final piece of the puzzle and lift the hood on the engine powering this entire system. Section 5, the mathematical matrix, the grid engine. To actually crunch the math, engineers use this super powerful yet simple tool called operator A. It's defined as a vector with the magnitude of 1, pointing on an angle of exactly 120 degrees.
It elegantly represents that absolutely crucial physical spacing of our grid, allowing us to mathematically rotate any current perfectly right into its proper place. And this brilliantly illustrates what happens when we plug operator A into a 3x3 matrix. It basically acts as the key to the whole kingdom. By taking our isolated 0, positive, and negative sequences and multiplying them by those A operators, we can fully reconstruct the chaotic real-world currents, or we can run a real-world fault backwards through this exact matrix to instantly extract those clean sequence components. It's an incredible two-way street of mathematical clarity.
Bringing it all together, the true genius of symmetrical components lies in rapidly isolating these three distinct sequences. The positive sequence gives us our healthy ABC baseline. The negative sequence acts as our saboteur, warning of severe unbalance and breaking effects. And the zero sequence is our escape artist, flowing straight into the earth to flag a line-to-ground fault. This exact mathematical translation is what allows protective relays to instantly isolate grid failures and restore order in mere milliseconds.
It's really just incredible to realize that the reliability of our modern, everyday world is maintained by this elegant math working tirelessly in the background. So, the next time a massive storm hits and the lights miraculously stay on, ask yourself, which sequence just saved the grid? Thanks so much for exploring this with me. Keep your curiosity sparked, and I'll catch you in the next explainer.